All right, so let's go ahead and actually jump into seeing one of these machines in action. Basically, we're going to try to design one of these things and kind of do the whole discussion piece. So we're going to live on this example for a little while. And then to drive it home a little bit farther, we're actually going to do this whole example one more time, but with a different approach. So we can begin this quest of compare, contrast to see all of the goodies come into play. So the language that we're going to try to build this machine for, so we're going to start with kind of these cheesy just language identification problems, is going to be the language of all bit strings. So here our alphabet is just zeros and ones. And what I want to play with is I want to play with strings that have exactly the same number of zeros as it does ones. They don't have to be grouped together. So this example of 0, 0, 0, 1, 1, 1 is grouped by zeros and ones, but I don't care how they're actually going to be organized. I just want these things to have whatever length it has to match on zeros and ones. So I have an equal number of zeros to an equal number of ones. So that's where we're going with. Any length though. So that's the tricky bit in all of this. If you were to try to design one of our earlier finite automatons to work with this language, it would fail miserably. I would recommend trying, just kind of like the palindrome examples that we did before. You could do it very easily for ones of length 4. You could do it for ones of length 6. You could do it for ones of length 8. But if you allowed any input length to happen, it's just going to come crushing down. It's just not possible. And you'll realize very quickly of the inefficiencies of the little finite automatons and the struggles that it would then have. So what it tells us is that we have to approach this in a different way. So we're going to be approaching this with these nice little Turing machines. Before we get into kind of the full Turing machine, tape, control unit, all that kind of stuff, I want you just to step back and think about kind of attacking this question as if you were back in CSC 150. So what that would look like then is your instructor, let's say it's me, gives you a list of length 6, and you have to tell me if the zeros and ones match up. So if that's all the instructions I gave you, I just said, okay, design some program that's going to count or kind of compare the number of zeros to the number of ones. Your first guess, or if I was kind of presenting this to a class, would be to probably come up with some counters. Maybe you would have 2 counters on your initial go. You'd have a counter for the zeros and a counter for the ones. And on your first pass, which would only take going across this list one time, so efficiency questions abound, if you were to read this thing across once, you'd actually see that the 0 counter would click up 3 times and you'd end up with a 3. And your 1 counter would click up 3 times and you'd end up with a 3 as well. So at the end of the day, you would actually see that the number of zeros equals the number of ones and that they both have 3 of them. Great, awesome, sweet. You passed 150, everything is great. You also might start to think about, okay, well, what if I don't want 2 counters? Maybe I only want just 1 counter. Well, hopefully you can start to see that you could have some kind of increment decrement process going on. And let's say we'll go down on zeros, up on ones. So as I read across this list one time, it's going to look like what? A -1, a -2. So decrement, decrement, increment, increment, decrement, increment. And I end up with a 0, which is going to say that the zeros and ones match up. So hooray, you improved it a little bit. You went from having 2 counters to 1 counter, and everybody's super duper happy. Yay. That's another way. It's great. It's awesome. It's not necessarily so great on a Turing machine. Totally is doable on a Turing machine to introduce this notion of a counter, in that you would just like move way over on the tape and begin kind of a nice little tally count of what's happening. But it's not necessarily ideal for our first go at a Turing machine, because that would involve a whole bunch of states and a whole bunch of extra stuff that I don't feel like talking about quite yet. So the way that we want to begin thinking about this is to think about matching things. So if this was a list of length 6, if you went into this, you could find a 0 and you can find a 1 and you could delete them from this list. So you say, okay, that and that, I'm going to remove them. Now I have a list of length 4, and you're going to find that 0 and that 1, and you delete them. Now you have a length of list 2, or a list of length 2, and you delete the 0 and the 1. Now you have a list of length 0, so everything then had to be matched. So that's the way that this Turing machine is functionally going to work, is that it's going to go through and it's going to grab these zeros and ones in pairs. How it does that, though, is up to some design aspect. You can go kind of with the 0 and you could go on the outside in, And you could say that 0 and that 1, and then you'd have that 0 and that 1. You could do what we just did of take the first thing that you find its friend. Take the first thing you find its friend. Take the first thing you find its friend. There are numerous different ways that you can actually go about the finding pair aspect. And that's kind of where I want to dwell on a little bit. So that's where I had mentioned we're going to approach this question twice. Once with option A, once with option B, and we'll give them the full Turing machine treatment. So we'll talk about how the Turing machine is going to handle it. And then we're actually going to build up the nice little state diagram that actually will showcase how everything is actually going to move and shake. We'll pull in some technology to show the nice little jumping from states to states to states, and then let this whole process just snowball out of control and play very nicely and kind of see what's going to happen.